So my name is Sanne. I came from Amsterdam in the Netherlands. It was a very long flight, but I'm very excited to be here. I'm a full stack developer. I mostly work with React and Ruby and Elixir. And I never studied computer science. I used to be an English teacher before becoming a programmer. So I was never taught about all like the algorithms and stuff. And one day I was curious how it's possible that you can just run a program and it can keep going without running out of memory. And it seems kind of magic to me. But really it's just, algorithms and code and other computer stuff. And if there's one thing we know from history, it's that magic is just science you don't understand yet. And I know there is not that much magic left in the world, and I'm very sorry, but I'm going to take away a little bit more, because by the end of this talk, hopefully, you'll have a brief overview of how garbage collection might work. How many of you do manage your memory by hand in their work? Do you ever worry about memory, garbage collection? Yes, I see one or two hands. Good, then you might already know what I'm going to say, but maybe you'll learn something as well. So imagine when you just move into a new house. It's all nice and empty and everything. But if you never clean up, your house will look like this. And you're going to run out of space. And the same thing can happen in your programs. You keep creating new objects and putting them in memory, and if you never get rid of them, you'll have a problem. So you could do this yourself, and let's think about what you would have to do to keep track of your memory use and your garbage collection all by yourself. First of all, you'd have to allocate memory. You have to tell your program where it can put stuff. This one can go in this cabinet, that one can go there. Then you need to figure out what you no longer need. And this is actually the trickiest part. Saying, put this in memory, that's fine. Emptying memory, that's also fine. The middle one is the hardest one. Because what you want to get rid of all your garbage. You want to free up all the memory that you can free. But you don't want to get rid of stuff that you might still need later. So, if you don't clean up on time, you run out of memory. Or in my case, I run out of shelves to put my books, because I buy too many books. But if you clean up too fast, you might break everything. And one of the things that you can end up with is something called dangling pointers. A pointer or a reference is kind of the address that something lives in memory. Imagine when you go to the theater and you give your coat, you get a little tag with a number. You can think of that number as the pointer. It is what will get you back the thing that you need. So let's say, for some reason, I have decided that this middle object, all these pink boxes are objects, by the way, of any kind. I say this is garbage, and I get rid of it. I now have a problem. In fact, I have two problems. If I need that middle object, well, it's not there. There's nothing I can do about it. There might actually be something else at that address by now. But I also end up with a memory leak, because I can never get to that last one anymore to get rid of it. So how am I, as a person, going to find this thing that I no longer need when I can't get to it? Luckily, we don't have to worry about this, usually. Most of us, I guess, work in languages where garbage collection just happens. And I'm going to be talking about 3 or 4 different ways of doing it, and I'll tell you a little bit about languages that use each of these as we go. Let's start with the simplest one, reference counting. Really, the easiest thing is, if nothing points to it, if we don't have the address of this thing, we can't use it. So let's say I have a variable and I give it a value node.js. My code samples are in Ruby, but it's all so simple that I'm sure it'll be clear. There's just no var or let anywhere. That's probably really the only difference. So I have my variable name, and I point it to nodefest. Nodefest gets an address, gets put in a little box. It's a little bit more complicated than that, but you get the idea. And then name points to nodefest. So one thing, the variable name is pointing to it. Then I have the very creatively named variable other name, which I will point to the same thing. Now nodefest has two references, so it's clearly still in use. We cannot get rid of it. Now I get rid of them by making them nil or null, I guess, as you JavaScript types would call it. And other name is also now nil. Nothing points to nodefest anymore, so we can get rid of it. And this is a nice way of doing it because it's pretty fast. You don't have to stop your program and go through everything. You can just get rid of whatever you don't need anymore as soon as you don't need it anymore. And Python, for example, uses this for a good chunk of its garbage collection. But it does have a downside. There are certain types of garbage that this can't deal with. And those are called cycles, which is when things point at themselves. So, once again, very creatively named hash or object, I guess, called A, which has a key other that points to nothing right now. So that has one reference. I have another one called B, but there the key other points back to A. So far, no problem. The first one now has two references, the second one only has one, and we're pointing it back. So now they each have two references. You might already guess what the problem is going to be. If I get rid of A and B, point those at nothing, there is still one reference, but I have no way of getting to this little cycle of these two objects anymore. So if I'm just using reference counting, it's just going to sit there forever. And that is why you might need another more difficult, not more difficult, different way of collecting garbage to make sure that you get everything. This one is called mark and sweep, which has as a downside that you do have to stop. You have to stop your program, go through all the objects, and then clean them. There are by now people who figured out ways that you can do it while your program is running, but those people are way smarter than me, and that is also way beyond the scope of this talk, so we're just going to focus on the basic idea behind it. So the idea is if you can't get to it, you can't use it. So I don't know about you, but at least where I'm from in Holland, every house has that one drawer that is full of junk and you can't find anything in it. You can kind of think of it like that. If the thing is all the way in the back of the drawer and you can't get to it, you might as well throw it away. So here we have a lot more objects. And what mark and sweep does, it starts with marking. It starts at the root of your program, at one or more roots. A root can be anything that you can always get to. Could be a global variable, for instance. I visit that and I say, okay, cool, I've visited this one. It is still alive. I'm clearly still using it. Then I go on. I follow all the paths out from this object, put them on a stack and go, okay, cool, you're alive, but I still need to visit you to see if you have any children. So we go to that one. All right, you're alive, great. Do you have any children? Yes, I have one child. All right, great, you are also still alive. And it just goes on until you've gone through your entire tree of objects that are in your program. And now, by logic, everything that I haven't marked as being still alive is dead, or no longer useful. They often call it alive and dead. I find that a little bit morbid, but it gets the point across. So all the black boxes are alive, the pink ones are unfortunately dead, and are now garbage. And you can see why you would want to stop your program while you do this. Because what if, I'm halfway through marking everything, and I suddenly create something that is, that's right here. But I've already visited that one. I'm not going to mark it, and I'm going to think that it's garbage, even though I only just created it. And then, for the sweeping part, the simplest way of sweeping is just going through the memory one by one, and for everything that was not marked, that didn't say, okay, cool, I'm still alive, cleaning that up. Ruby uses mark and sweep, but it uses lazy sweeping, where it marks everything and then sweeps only enough to keep going. Node v8 actually also uses mark and sweep for a part of its collection. It uses something else for the other part, but I'll mention that when I get to it. And as you can see, you don't want to do this one too often because you have to stop everything, which is why the V8 engine only uses this for a small chunk of its collection. A downside of this is that you end up with lots of little chunks of memory. Because let's say I'm going to make something really big and I need 3 bits of memory next to each other. I don't have them. And that brings me to the next collection algorithm, which is called copying collection. I've also heard it be called scavenging, which is, I don't know, maybe a more interesting name, but copying collection really tells you what it does. So to do this, we divide our available memory into 2 separate heaps. Here we have the top one, which is full and about to be collected, and then the bottom one is nice and empty. Because that is what you always do. You always create your objects in one of the spaces, and the other one's always empty. So similar to mark and sweep, we're going to trace from all the roots and find all the objects, but instead of marking them, we're going to copy the ones that we find. So the first one's still alive. Great, we're copying it. So is number 2, number 3, number 4, number 5, number 7. Those are all our live objects that we found. You can imagine that we traced them the same way we did with the marking before. And now you see we have those 3 free bits of memory right at the end. Nicely together, ready to put a big thing. But now, we can easily those are all garbage, but we've also copied the other ones, so we can easily just empty out that whole other half of memory and move on. An upside of this is that it's pretty fast because we're doing the marking and the cleaning up in one go. The other benefit is, that, like I said, you keep your memory together. The downside is that you only have half the space available. Because you need to divide your memory into 2 separate heaps to do this, which means you have to do it more often. This is the other algorithm that the V8 engine uses for another part of their garbage collection. They call it scavenging in all the literature that I read, so it actually took me a while to figure out that this is what it meant. It's a variation on this. Turns out that if you Google scavenging, you don't really get much computer science. But this is the basic idea of what their other system uses. So as we've seen before, some of these garbage collection algorithms, they have to stop your program, they take a while, and then, so you don't want to do it too often. And you don't want to have to check everything all the time. And luckily, you don't have to do that. Because you can divide your memory into generations. And this is actually quite interesting because there's a pretty strong indication that by far most objects that you create only live for a very short period of time. Anywhere between 90 to 97% of the objects that you create become garbage very, very quickly after. So those objects that do survive are probably important. Think of it like if you're requesting a website, a lot of stuff has to happen on the server, but also in the browser, to actually like show you this page. But once the page is there, all that stuff is no longer useful, no longer important. But other things, like the router or other, especially server-side objects, are much more important, and they exist for a very long time. And that is the idea behind generational collection. You have a young generation that you collect very often, and then an old generation that you only collect every once in a while. Here we have an example. Once again, you have to divide your memory into 2 or more generations. Python uses 3 generations. I'm pretty sure V8 uses 2 or 3. Either 2 or 3, I'm not 100% sure. And the idea is as follows. Every new object that gets created ends up in this new object space. And when that fills up, or when a certain amount of objects have been created, you will collect only that generation. And when it fills up again, you collect it again. And then, at some point, you will copy the objects from the new generation to the old generation if they've survived 1 or more cycles of garbage collection. Whichever way they got collected. They were scavenged or reference counted or whatever. And to give you an idea of just how big the difference is between these generations, in Python, they collect the youngest generation when 700 objects have been created, and the older 2 generations already get collected after 10 objects. So the difference, this idea that objects become garbage really, really fast, there is a really big difference between what gets cleaned up almost immediately and what stays around for a very long time. Like I said, V8 Node also uses generational collection. And so what they do, they have 2, maybe 3 generations. They use the copying algorithm that I described earlier on their new generation. So they just go through everything and they copy everything to the new space. And then if they realize that, oh, I've copied this one already once or twice before, then it gets copied to the old generation instead, where it just, hangs out until the old generation eventually gets collected with a full mark and sweep algorithm. And it turns out that I've been speaking way, way faster than I thought I would. Because I am already almost through my material. And when I practiced, I was like, oh, 25 minutes, this is pretty good. But I'm talking very quickly, apparently. I'm very sorry about that. So I do hope that maybe you have some questions for me. Because, like I said, I hope garbage collection is no longer magic. I don't remember what I was going to say. I hope garbage collection is a little bit less magic, and I do apologize for speaking way quickly. I hope the translator could keep up with it a little bit. Does anybody have any questions or anything that you want to know a little bit more about that wasn't entirely clear? Was I that clear even though I spoke so fast? I'm glad the translator at least could keep up with me, even though I could barely keep up with myself. Well, thank you very much.
はい、ありがとうございました。そうですね、GC の話ですごくなんていうか分かりやすいというか、概念的な話から入ってその後詳細的な話に入ってくれるのですごく分かりやすかったです。ちなみにこういう GC だけを解説した話ってなかなかないというか、割と面白いんですよね、今日この話。 今どうやってやってるかとかも結構あるので、ちょっと時間あるんで、もしあれだったら、if you have some any question to her, so please raise your hand. No? So Japanese engineer is very shy.
We're just going to talk to me one-on-one, that's all fine.
Yeah.
Thank you. Your decrease JavaScript file trash file. Indeed, if I try decrease my JavaScript project, I will decrease what will I decrease percentage? I don't know decrease method.
So your question is what you can do already to use less memory?
For example, web service, I create to use JavaScript, node.js. I have not decrease JavaScript object. Yeah.
No, normally you wouldn't have to worry about it, right? Because this all happens for you. Honestly, I don't really know what I would do if I ran out of memory, but I do think that one talk later today is about finding a memory leak in Node.js. Because I saw that, I was like, oh, that's interesting. That kind of fits with mine. So I don't really know, but I'm guessing that guy does know. Is that you? Oh, yeah, he's in the back right there.
多分なんですけど、解説しちゃっていいですか。JavaScript のオブジェクトのメモリーを減らそうとするのはどうやってやったらいいですかっていう質問と、自分実際にあまりそんなことしたことないんだけど、そんなことした方がいいのかどうなのかっていう話ですね。で、彼女の解説は、ガベージコレクションでやってくれるから基本的には大丈夫です。ただ、メモリーリークって呼ばれている、その JavaScript の中で GC が、うまく働かない現象、グローバルにオブジェクト持っちゃうとか、メモリーのリークを意図的にプログラミングのバグで起きちゃうかもしれないっていうのがあって、そのメモリーリークに関しては、その次のセッションでメモリーリークに関するセッションが実はあります。で、He will talk about the memory leaks。なので、それも聞いてみてくださいということですね。はい。どうもありがとうございます。すいません。質問していただいて。で、残り5分なんですけど、じゃあ一回休憩にしようかなと思います。じゃあ何かあったら。